Then I will be covering the topic with respect to the combustion in diesel engines today. We have seen the combustion in SA engine, how it is happening. It's not only in SA engine but also in diesel engine. So it is for anything you need to have oxygen and the temperature fuel to burn to get the temperature. So we have seen this. Air and fuel mixture is very much important, and air contains oxygen. It will help for burning, and combustion will take place. This phenomenon is common in both SA and CA engine. Then we have seen what is combustion and combustion process. We have seen the chemical formula, and this is very much important. So I told you this diesel is heterogeneous in nature, and here the mixture are non-uniform, and the gasoline is a homogeneous mixture where the mixture are distributed uniformly. So we have seen the dependent parameters on the combustion. We have seen the stages of a combustion in a SA engine. In how this air fuel ratio also affects your catalytic converter efficiency. We have seen the actual combustion stages in SA engine and the practical theoretical one and the practical one. We have three stages: ignition lag stage, the flame propagation stage, and after burning stage in the case of SA engine. So we have two type of combustion. One is normal combustion and abnormal combustion. This will happen both in SAS also and also in CA engine. So when the flame is traveling uniformly and evenly across the combustion chamber, then you get the normal combustion. And when the combustion gets deviated from the normal behavior and resulting in the loss of performance or damaging of the engine, you get abnormal combustion. This is common in both the SA and also in CA engine. Okay, so both the SA engine and CA engine, you have normal combustion and also abnormal combustion. Abnormal combustion is basically not good, and it will lead to the damage of the engine and also the loss of performance. Basically, the performance here indicates the power or the torque of the engine and the abnormal behavior. Basically, you get a sudden explosion in case of abnormal combustion. You get a sound called knocking and or detonation. So I will explain that today. So now I will explain about the knocking and pre-ignition, and I will show you one video. After that, we will see the combustion in diesel engines. Okay. So the phenomenon of knock in SA engine. Okay. So this is the normal combustion. It consists of the ignition, and then once the ignition starts, then you have some delay, and after the delay, your pressure gets footed up, and expansion occurs, during which pressure comes to the dead phase. Here, uh, when you say the normal combustion, what happens is the flame is going to travel across the combustion chamber from A to D. This is the flame. Let me assume this is whenever the fuel and air gets mixed up, or fuel and oxygen gets mixed up, you get a flame. So this is the flame. You assume that this is a flame having some distance. Here to D is the distance. So in the normal combustion, the flame always travels from the point A to point D. You see here, when you are advancing the flame, when you are advancing the flame, and when the flame is towards the end, this is the end, okay? When the flame is getting advanced, and when it is reaching to the longest distance, and when it is going to the towards the D, is it is approaching nearer to the point D. What happens is there is a flame which compresses the charge, the end charge. This is the end charge. BB dash and D is the end charge, and this will rise its temperature. So you have the spark plug, okay. When this flame is nearing to the location of where the spark plug is there, then it raises its temperature, but it will not auto ignite. It will not ignite the spark plug. Okay, and what happens is only the temperature will get increased, but that temperature will be lesser than the auto ignition temperature or the self ignition temperature. And you have the diagram of the, the timings. So before TDC, first stage is the piston moves from TDC to PDC. The air fuel mixture comes into the combustion chamber, and during the compression stroke, the air and fuel gets compressed, and before the end of compression stroke, which means before the piston reaches the top dead center, spark gets ignited, and that will help for a combustion. Okay, but what happens is this happens in a normal combustion stage. There is one abnormal stage, which I will explain that abnormal stage is nothing but knocking. See, now I will talk about the normal combustion. So when the piston moves from PDC to TDC, it compresses the air fuel mixture in the case of a SI engine. So here, if the temperature of the end charge had not reached its self ignition temperature or auto ignition temperature, the charge would not auto ignite. The flame will also advance further and consume the charge BB-D. So this is the flame distance here D. So when the distance moves from BDC to TDC, the flame, this is the cross-sectional view actually. So you don't get confused. I will explain that with the help of video also. So you can imagine that this is the flame cross-sectional view, and the flame is having some distance, okay. Uh, and when the distance is nearing towards the end, still when it is reaching towards the end, still the charge or the flame will not have been reaching the self-ignition temperature, and the result, you will not the flame will not auto-ignite, and still the flame will further advance, and it will also consume completely the charge. So and again, this will help for the normal combustion as per the phenomenon, normal phenomenon. When you go for the abnormal phenomenon, what happens is you have the abnormal combustion, means you get a sudden peak pressure which is not normal, and it will be higher. The peak pressure will be higher than the normal combustion pressure, and you get the noise called a knocking sound. This phenomenon is called as a knocking phenomenon. So how this will happen? So this is the flame I told you that is having the distance here to T. Before it reaches the certain distance, what happens is the spark plug will ignite, auto ignite. Okay, and as a result of that, when ignition happens in the spark plug, what happens? This ignition will also create a combustion because the spark plug creates a fire, and again that fire when it is reacting with uh, the mixer. The combustion chamber is this is the combustion chamber. Is the combustion chamber in which air and fuel mixer is there. So when this spark, when it ignites, that ignition when it is reacting with this air and fuel mixer, it also creates a combustion. Okay, combustion is basically occurs when both air and fuel and the mixer is when it is reacting with the ignition. What happens is you get a combustion at various multiple points. So here also you are going to get a combustion which will travel from right to left, and already the flame is traveling from A to B. So one flame is going towards the direction A to D. Another flame is traveling from D to A. So you both this flame will collide each other. Okay. So when these two flames are colliding or touching each other, what happens is you get a sound that phenomenon you call it as a marking. So and here what happens when the flame travels from A to D, you follow my cursor now. Moving the flame is traveling from A to D, but before it reaches certain point, uh, auto ignition will happen or self ignition temperature will happen. As a result, the spark plug will ignite. Uh, when the piston moves from BDC to TDC, say for example, the spark ignition will happen or the ignition will happen 50 degree before TDC. Okay? But what happens is instead of 50 degree before TDC, there is a possibility well ahead, even when the BDC is in half the stage of the position, or the 40 percentage of the position, the spark will ignite at well in advance. As a result of that, it also creates a combustion in one direction, and the normal combustion is also happening in another direction. So it creates a phenomenon called a knocking that creates a sound called knocking sound. Okay, so here what happens is a second flame develops and it moves in opposite direction where the collision occurs between the flames. So one flame here and another flame here. Uh, so you might be knowing and worrying what is this CC dash. This happens. The CC dash will happen during the abnormal combustion. So here the end charge BP dash reaches its auto ignition temperature and remains for some length of time equal to the time of the pre-flame reactions. The charge will also auto ignite, leading to combustion. This is what I told you. Even you get some time. So in the normal combustion, what happens is the auto ignition temperature will not happen, and it will happen only when the piston reaches 15 degree or 20 degree before TDC. In the case of abnormal combustion, it reaches well the self-ignition temperature or auto-ignition temperature reaches well in ahead. And when it reaches well in ahead, what happens is it remains for some length. Okay, it remains for some length in the sense still you have some length which the ignition will be remaining. means it remains for some particular distance, and during that distance you get the knocking. So lesser the distance, you do not have the knocking. Uh, so when you have the pre-flame reaction, the flame is going to happen in another opposite direction also. So you see here there is one more charge. This is a cross-sectional area, CC dash. Here the charge ahead of CC dash would ignite. So in a normal combustion, the ignition will happen only at this particular point. But in the case of abnormal combustion, what happens is you get the ignition. It can be 40% of the position, or 50% of the position, or even nearing to this. Even if the auto ignition happens even at this point where my cursor is there, before the CC does, even then there is a possibility the opposite flame can create that will lead to a phenomenon of a sound called knocking sound. And again, the intensity of the sound in terms of the decibel will vary. If the auto ignition is going to happen at this point in time, so you get the other flame in the opposite direction where the distance is going to be lesser. So you get the intensity of noise is going to be lesser. But assume that the flame is moving from the mid position, or 50% from A to D and D to A. So the velocity at which both strikes is going to be higher. You get the high level of sound. What will happen because of this knocking? You have the damage to the piston. Okay, because combustion is all about happening in the combustion chamber, which is about a piston bowl, and this detonation or this knocking will create the impact to the piston, and result of that, the severe knock is going to happen that will lead to the damage in the piston, and the piston crown. Piston crown is the top of the piston, and even the cylinder gasket is going to get the issue, or the burning issue. The, the losses can happen, can lead to some leakage also. If the knocking is going to happen in more time during the course of operations, and even the cylinder head is going to get damaged. So these are all the effects that you are going to get out of the knocking. So there is one more term called the pre-ignition. It means the ignition will happen well in advance. This ignition will happen when it comes in contact with a hard surface in the absence of spark. So this phenomenon is called as a pre-ignition. And again, this pre-ignition is initiated by the overheating the projecting part. It can be the spark plug electrodes. When it gets heated up, you get a pre-ignition. Even this knocking is also because of the pre-ignition. Okay, because you get a pre-ignition. That because of that pre-ignition, you get the combustion in the opposite direction. The flame is traveling in the opposite direction also. And even you can heat the exhaust valve head, and when you heat that, when you apply the hard surface to the exhaust valve, even then you get a pre-ignition. Even the auto ignition or the self ignition may also overheat the spark plug, and even the exhaust valve will remain in the hottest temperature, and that will self ignite and creates a phenomenon called pre-ignition. So this pre-ignition, what happens is it will reduce the engine efficiency. Even as I said, the power and torque is going to get less, and when that is lesser, your complete efficiency of the engine is going to be lower, the mechanical efficiency, the thermal efficiency, and the combustion efficiency, all this going to be lower. And this even the pre-ignition also causes faults, which will also result in the melting of the pistons, and even the spark plug also gets melted away. This because of the pre-ignition. What happens? It creates a temperature, and even it will also overheat the spark plug electrode. Spark plug is having the electrode, and that spark plug electrode will get overheated because of the ignition, and finally it will also lead to the damage of the piston, and ultimately the engine get failure. So this is how the piston looks when you get the pre-ignition. Okay, so now we'll see one video with respect to the knocking and the the, the pre-ignition kind of thing, and then we will go with the next topic called the phenomenon of combustion in diesel engine. So this is the video about knocking in pre-ignition. So I was telling during the regular combustion when the piston moves from TDC to PDC, your air and fuel gets mixed, and the piston moves from BDC to TDC, the air and fuel gets compressed, and when the piston is nearing to the top dead center, the spark gets ignited, and that will happen in the normal combustion. You see, when it is nearing to the top dead center, you're going to get a spark. The result of that combustion will happen in the normal combustion. That is the regular combustion. This is the air fuel mixer. How it looks, and it is compression is happening. Again, you get the combustion. This is a regular phenomenon. Uh, okay, so now you see the next phenomenon is the knocking phenomenon. Uh, uh, so I told you the charge. Okay, the CC dash. Okay, that is the limit. Uh, Here, what happens is the knocking can happen even when the piston is this position or even at this position also. So before it reaches a particular point, uh, because of the temperature, uh, you get the pre-ignition kind of thing, and as a result of the pre-ignition, what happens is the electrode spark plug gets heated up, and the ignition will happen. And here the spark will not happen, but the ignition will happen. That ignition will create flame, will create a combustion. Basically, the combustion, when you have the combustion, it is nothing but a flame. Okay, it propagates. It will propagate from the top position to from the top region to the down region. Already there is a combustion or flame is which is happening from the bottom to the top. Okay, so these two flames will collide. That you get a sound, the knocking sound. Here the movement is very slow to understand or to make understand that uh, the pre-ignition is happening before the. You also seen in the wall timing diagram that 15 degree or 20 degree before the TDC is the ignition for a gasoline engine. So what happens when it is before 20 degree or 40 degree or 50 degree? What happens? Uh, that is where phenomenon of knocking comes into. That's why the wall timing diagram is very much important. See, we can read this the theory. So with knocking, what happens? The initial ignition of the mixer is initiated by the spark plug. But here you do not get a spark, but you get the ignition. It is caused by the combustion pressure and the temperature. A spontaneous combustion of the mixture occurs. So here a second, almost a parallel combustion inside the cylinder will happen. When both the flame front hits, the intensity or high frequency pressure waves are produced. The output, what you are going to get out of is a sound. These pressure waves create the characteristics of a metallic ping sound. Okay, and the cylinder pressure increases dramatically. And again, I showed you some of the peak pressure, the temperature, the cylinder pressure gets overshooted, and the knocking combustion can also lead to the pre-ignition because of the high combustion temperature. Okay. See, knocking will lead to a pre-ignition, and vice versa also. So here a glowing spot somewhere in the combustion chamber is most likely a point of for a pre-ignition to occur. So if you have any glowing spot anywhere in the combustion chamber, uh, and this is a starting point for a pre-ignition to occur. And say for an example, uh, you know, it is the fuel is having the carbon hydrogen chain in it, and a carbon can ignite a charge while the piston is very early in the compression stroke. So that is where it happens in the pre-ignition, and this will happen. Pre-ignition will happen uh, even 50% or 40% as the top knocking how it is happening. So the knocking is going to happen because of the pre-ignition and vice versa also. And what happens? You need to ensure that you are following the timing diagram. And even the timing also will vary from engine to engine and configuration of the engine. And even the OEMs they follow different wall timing diagram. Let's say you have some buffer. When I say 15 degree, it is not exactly 15 degree. You also have 15 degree or 20 degree before TDC. The ignition will happen. Even in the case of diesel engine, also same phenomenon you need to follow. Uh, See, one method how you can reduce knocking is that by increasing the octane number. You have octane number for a gasoline and cetane number for a diesel. When you increase the octane number of a gasoline engine, of a gasoline fuel, what happens is the knocking effect or the knocking phenomenon can be avoided. But again, there is also a pros and cons with respect to the increase. Uh, and this octane number, and again, even when you increase the flame speed, uh, the flame when you increase the flame speed, what happens? The distance between A to D, what I was shown, A to D, the time taken to reach the flame to reach A to D, when the flame speed is higher, will be very much lesser. Uh, when the flame speed is higher and the time taken is lesser, then you give a very minimum chance for the auto ignition or self ignition to take place. Even by increasing the flame speed, also you can reduce the knocking effect in an engine. It is very important to use the proper range of temperature and heat. The temperature and the heat will also heat the electrode of the spark plug. Okay, that will also lead to a pre-ignition. So this is spark plug having the electrodes. Uh, even the length, and you have the electrodes in the spark plug. So even to prevent pre-ignition, it is important that you need to have the tightening torque properly for the plug. And again, you need to have the spark plug that should be carefully matched to the recommended heat range. So if the heat range is going to be higher, that will also lead to the pre-ignition. You see, the effect of the knocking and pre-ignition, finally you get a damage to the piston. You can see because you're going to get a load continuously into the piston. As a result, the piston will get damaged. If the piston is getting damaged, what happens is your engine is going to get seized finally. You can see there is some discoloration. Okay, discoloration is happening. You see how it looks. Okay, this again they lead to some point where you also get a, you can see also see the piston ring is slightly getting the breakaway. Okay, this is the top ring, and again finally it will lead to the seizure of piston and the engine finally. Okay, uh, so you can also reduce the air intake temperature and the pressure. Basically, inlet pressure. When you reduce the inlet pressure, what happens is the air when it is entering into the mix combustion means the fuel. Result of that, when the pressure is less, the temperature is also going to be lesser, and there is a possibility that can avoid the self-ignition or auto-ignition. Thereby, you can also reduce the, the knocking. And even you can also reduce the compression ratio of your engine, of your gasoline engine, to avoid the knocking. So, the compression ratio maximum it comes 10.5 is to 1 or 11, maximum 11 or 11.5. Beyond that, in the case of a gasoline engine, you get a knocking sound or a knocking phenomenon. So when you even when you reduce the compression ratio, you can also reduce the knocking. And even when you reduce the temperature, when you reduce the pressure, temperature is going to be lower. And when the temperature is going to be lower, the peak temperature is also going to be lower. That will also reduce. You see here, in the earlier days, they are also using TL, tetraethyl, that is the additive which is been added into the gasoline fuel to avoid uh, this type of knocking. And even you can also have the octane number higher. Okay, so these are the content as per your course handout. I will be focusing more towards analysis of cylinder pressure data, fuel spray behavior, ignition delay, and the stages of a combustion. You also have different models. In the simulation models also you have for a C engine. I'm not going to cover that. But in due course of time, maybe I'll send you some of the material. Uh, but today class, I'm not going to cover that. Uh, so this is the stages in C engine, which we have seen it already, but we will see it more in a more elaborate manner. Even I have asked this question in your exam also, for a makeup exam. So here, basically, you need to draw this and you need to explain overview, but not in detail. So now I will explain you in detail about this engine, different stages. Basically, we have 4 stages. The first stage is the ignition delay period, which will happen after the start of ignition. Next is the pre-mixed combustion phase, where and the air and fuel gets pre-mixed. Again, get a mixed one where air and fuel gets completely mixed, and get a end of injection. That comes to the pressure comes down. When the pressure comes down, your heat release, rate of heat release also going to be lower. Okay, so this is the first stage. First stage is the ignition delay stage. So the first, what happens? The fuel is getting injected directly into the cylinder towards the compression stroke. So again, the valve timing diagram comes here into picture. So when the piston moves from TDC to BTC, here the case of C engine, only air comes, air mixer, air alone comes into the intake into the combustion chamber, and when the piston moves from BTC to DTC, the air gets compressed, and before it reaches target center, fuel will be directly injected into the cylinder at the end of the compression stroke, and again the fuel and the air gets mixed up, and, you have some delay period. Okay, that delay period you call that ignition delay period. So what happens when air and fuel gets mixed up? You get a penetration if the flame gets penetrated into the combustion chamber. Again, the fuel is going to get out of the fuel injection. You get a fuel out of it. It evaporates. The vaporized fuel will mix with the air, you get the flame with a high temperature and high pressure. And the next phase after the ignition delay starts, what happens? Your peak pressure going to be higher, and the rate of release is going to be higher when air and fuel gets mixed up, and the fuel is come from the fuel injection system. And once the fuel gets injected, this fuel will react with oxygen, which is present in the air, is there with high pressure, compressed pressure. The piston moves from BDC to TDC, and that also having the temperature in it. So this temperature and the temperature which you are going to get out of the flame or out of the combustion, that finally will result in the overshoot of pressure. When the pressure gets overshooted, the rate of heat is also getting higher. This is what explained in the diagram. So next phase is nothing but uh, the pre-mixed combustion phase. But in the ignition delay period, you get the point A to B. This is the ignition delay period. In the case of ignition delay period, you will not get the peak pressure, but it will try to form a peak pressure well before this also. Even it will try to form a peak pressure at this stage. At this every stage, each and every stage it will try to form, but it will not form. Okay, because it needs to have some delay. Okay, even if you reduce the delay period also, ignition delay period also, we have the advantage of reducing the knocking or the detonation, right? And ignition delay period is going to be slightly higher in the case of gasoline engine. But irrespective of that, it is very difficult because you need to have some time for the pressure to rise or to shoot up. And again, when you inject the fuel, it needs some delay. That ignition delay can be a physical delay or a chemical delay. We have two type of delay. I will explain that after the stages. After I explain the stages, I will explain what is physical delay and what is chemical delay. And that this two delay is increasing this time, this distance. I will explain that after explaining the stages. Okay, the next stage is the pre-mixed combustion phase, P2C. So here the combustion of the fuel which has mixed with the air, here you are going to get high pressure, high temperature, and which you are going to get out of the ignition delay period. Um, and this will happen with respect to the crank angles, which is explained in which is shown in x-axis. So here air and fuel gets pre-mixed, and when the next comes the third stage called the mixed controlled combustion phase called C2D. So here the complete combustion of air and fuel gets completely mixed up here in the mixed controlled combustion phase. And here the burning rate is controlled primarily by air and fuel mixer. When you're controlling the burning rate, what happens is you are going to reduce the pressure, and as a result, the rate of heat is going to be lesser in the controlled stage. And the last stage is nothing but the later combustion phase. So that you call it as a phase D to E, where the heat release or rate of heat release may proceed at a lower rate well into the expansion stroke, which means no additional fuel is injected during this phase. There is no fuel injected here because you're going to inject the fuel injection going to end here, and no fuel is going to get injected here. As a result, your pressure comes to the very low stage, and your heat release is also going to come to the low stage. Okay. I will explain that with respect to some additional points also. So, the heat addition is going to happen both SA engine and CA engine. So, now I'm going to compare the occurrence of the event between a heat addition which is happening in SA engine and CA engine. Uh, so, I'm comparing a child with a teen. So, the occurrence of a heat addition in the case of SA engine is like a child care event, whereas occurrence of heat addition in the case of CA engine is going to be a teen care event. Okay, so this is how the ignition will happen in the case of CA engine and how the ignition is going to happen in the case of AC engine. The ignition point you can see it is much more rapid in the case of AC engine. Even though it is homogeneous, you can see how the red the intensity of the red color you see is too high. And you can see the ignition point, the intensity is less in the case of CA engine. So this itself is a reason why the reason how the knocking is much more higher in the case of a gasoline than that of a but again, there are some few points you can reduce the AC engine knocking by increasing the octane number of the fuel, and you can also add additives. But that additives will also have the impact on clogging the piston. Also, sometimes it creates a clog the air fuel. Also, like it creates a stopping point for the mixer as well. It leads to a clogging effect. It has both pros and cons. Even you can reduce the compression ratio. But one advantage is since travel speed is going to be higher, the piston moves from the speed at which the piston is going to be higher, and you have less emission delay period because of the engine also reduce the noise. The flame propagation. I was telling you the flame propagation C to D in both SA and CA engine. The flame always travels like this. Okay, this is the cell. This is the shape of the flame. Okay, irrespective of CA or SA engine, this is going to be the same. And the fuel droplets is going to be like this. And then once the fuel and the oxygen gets mixed up, then you get the burning. The flame gets pumped. The fuel vapor is the fuel vapor, and oxygen and hydrogen. And oxygen content is there in the air. This is the vortex. Vortex is lemons. This is swirling in how this is going to form. Vortex is the head of the vortex. Uh, this head. This region you call this a vortex region. You can see the temperature at which when the distance is getting increased. First is cold fuel. The fuel alone comes at this stage where the temperature is going to be 350 Kelvin. And here you are going to get a warm air. When it is reacting with the fuel, you get the temperature is going to be 90 Kelvin. And here you see this is the rich mixer. Rich mixer means more fuel because here the fuel is going to be more. Okay, because the engine base, this is the fuel. Okay, where the fuel is going to be more and the air is going to be lesser. So and then you get the 25 Kelvin mixer. And when it goes the next stage where the air is going to get when the person moves from BDC to DDC, the air is going to be here, get a complete mixture. And here the temperature is going to be 1600 Kelvin. And here this is where the combustion particles also comes carbon monoxide, hydrocarbon, unburned hydrocarbon, particulate matter. All this comes here in case of diesel engine, and you get all this pollution. I mean, the exhaust emission is going to come of NOx, CO, But I also told you about treatment, how you can reduce NOx, carbon monoxide, hydrocarbon. But it is very necessary to go for a multiple injection strategies and other aspects even before go to the after treatment. Here the temperature is going to be the vortex. This is the head I told you. The temperature is going to be 2007 Kelvin. This we have seen these types of cylinders for a engine. We have seen in the previous things also. Just a small recap. You have a direct injection. It can be the form of spill in the combustion chamber, or it can be the, the chamber is of quiescent chamber having the shape like this. And you also have pre-chamber and the main chamber, where you this is the pre-chamber where you ignite at where the initial level of the combustion, the pre-chamber will happen at the pre-chamber. You have the spark or the ignition will happen here, and when you get here the initial level of combustion at this stage, and again the second level of thing will happen in the main chamber. But this is indirect injection, so, and it's not that much effective as a direct injection. But you have the advantages also when you go for indirect injection as well. You also have an advantage, but uh, it is always better to go for a direct injection. So when you go for a direct injection, uh, this is how the phenomenon is going to be. When you go for a indirect injection, uh, the phenomenon is going to be slightly different. Where sometimes the temperature you may not reach to the expected level, but still this is also a quite a good one. So this is also a good method to reduce the NOx as well, because when you are reducing the temperature to the help of the pre-combustion chamber, so definitely the overall temperature what you're going to get here is going to be lesser. You reduce the peak temperature, your nitrogen oxide emission is going to be lesser. But this nitrogen oxide emission will also lead to high particulate matter. Okay. So again, there is also a pros and cons. So it's always best to go for a multiple injection strategies. Okay. So this is the modeling of a combustion system in a CA engine. So basically, CA engine is a much more the teen stage. It's not like a SA engine like a child one. So here these are the parameters that we need to consider. So the injection rate at which the fuel gets injected, the spray pattern, and the piston kinematics. So the piston moves from PDC to PDC, PDC to PDC, the piston movement. Okay, even that will also play a vital role in the combustion. The fuel you are going to get in the combustion chamber. Instead of that, you are going to get a turbulence. Okay, the spray and turbulence is going to be the very important point of view with respect to the event occurrence in the case of a combustion phenomenon in the case of a C engine. And you're going to get a spray from the injection, and hence you need to control the injection rate. You need to have the optimum control rate of injection. And when you get a spray, the fuel you are going to get, that fuel gets sprayed into the air. The air and fuel gets mixed up, and again the volume, the spray volume is also very much important. And again, this will entrain into the air mass, and you are going to get a pre-mixed combustion at the initial stage, and then you're going to get a diffusion combustion or complete combustion or the controlled mix, what you call in the second stage. Uh, Stage is a pre-mixed combustion. Next, you go for a complete mixing, uh, where you're also going to have a diffusion combustion, where both air and fuel gets diffused with the help of a swirl, with the help of a turbulence, with the help of the kinetic motion. And you also have the vaporization coming from the injection. Vaporized fuel also you can also use electronic fuel injection. So the electronic fuel injection in the form of the vaporized one, even that can be used for the combustion process to take place. So irrespective of the premixed or the complete mixer or a diffusion or a vaporized fuel combustion. So irrespective of the type, whatever you have, the output what you are going to get is a heat release rate or the peak pressure or the pressure as an output. So the input is the injection rate, the kinematics of a piston as well, and even the spray pattern and the turbulence. All this will give you the output of the combustion. This is a thermodynamic process will happen in the case of C engine. This is all these things all you need to consider while you're going for any modeling. Uh, Before you put the system into the system, you need to do the simulation modeling thing, for which all these parameters are very much important for doing the analysis. So this is the in-cylinder process which is going to happen in a diesel engine. It is similar to what had been explained with respect to the crank angle versus heat release rate. But it's in this graph, the mass flow rate of the fuel and also the air is also taken here. The result when we are analyzing the in-cylinder process, means inside the cylinder, how the diesel engine is going to process. Okay, when you're considering the mass flow rate of the fuel and then heat, how the heat is going to get developed. So always you have the injection and also you are going to start the injection here. Once you start injection, you're going to have some delay, and the delay you're going to start the combustion. During the start of combustion, your peak pressure is going to be higher, or the heat release is going to be higher because the mass flow rate of the fuel is going to be higher. Okay, you see, this is the mass flow rate of the fuel injection, whatever it is getting indicated, is going to be higher. And next it comes to the phase called the complete mixture of air and fuel gas comes mixed here. Uh, and this is the output in terms of the quantity, the heat in terms of the output, work output. And the work output is going to be lesser. So you see, this is whatever mentioned in the thick is nothing but the output, the work output basically. The work and heat can be a good thing. You can also compare the work and then heat. When work output is going to be higher, the heat whatever is going to get generated is going to be higher. So for time being, I'm going to consider the Q as a heat. The heat, which is nothing, which will give you the work output. Even we have seen the work done in the case of the auto cycle and diesel cycle. Even we have done the, the efficiency, air standard efficiency of the auto cycle and diesel cycle is going to come out of the work which is carried out. Again, that again work is also correlating towards the heat supplied and heat rejected. We have seen that while doing the big mean effective pressure and also the air standard efficiency for the auto and diesel cycle. The same applicable here also when you're going for a modeling or a simulation of a diesel engine, you need to understand the in-cylinder process, how it is going to happen, for which you need to understand the mass flow rate of the fuel and the air. Even the air is also very much important. And even what will be the heat output which is coming out with the help of the work carried out with the help of the reaction of the fuel and the air. Uh, this is the when I will tell in three different phenomena. First phenomenon with respect to mass flow rate of fuel, which is highlighted in the line with some dots. Next phenomenon is with respect to the heat, which is highlighted with the thick color, and the last phenomenon is with respect to the pressure. So already I explained about the pressure, how it will vary with respect to the heat release rate. We have seen the four stages. So during the four stages, uh, uh, how the mass flow rate, how the mass flow rate of fuel and the heat will vary. So here the mass flow rate of the fuel will not be there during the injection delay or ignition delay, and it will be there during the pre-mixed stage, and during to the mixed stage it comes to the directly to the zero level. Okay, and here when it comes to the zero level, you are going to get the end of injection. When see when you don't have injection, basically the mass flow rate of the fuel is going to be zero, but it's shown in the drawing with the dot. And again, but even though you don't have the fuel, you have the work. The work is going to get happen. The heat will be there. It is what shown here, and it will happen up to the dead phase. Heat release rate, pressure, uh, the work done will all be very much important while we're going for a in-cylinder process analysis. So you also have some problems in the case of the diesel engine. Going to get some combustion problems. Um, the combustion problem can result in the burnt and eroded piston crown. Even the piston ring can get fractured. Even if you are not analyzing all these phenomena, there is a possibility this type of problem can occur in the case of diesel engine. And even you get the whole piston crown also. And even the piston ring can jam into the bolts. Okay, the piston ring you cannot it will not come out. Even that type of problem also you may experience. Okay, so we'll see the ignition delay, which is very much important. So how this ignition delay is being defined? It is defined as the time or the crank angle interval from where when the injection starts to the onset of combustion. Okay, before the time what you see here, when the fuel injection starts, you will not get the combustion immediately. You have some delay for the combustion to take place. That delay period you call it as ignition delay period. And this ignition delay, I told you, you have because of two process or two delay. It can be a physical delay or a chemical delay. This physical and chemical delay or process must take place before yes, before you see, this is very much important. Before a significant fraction of the fuel chemical energy is being released. Okay, this must take place in a fraction of second. Both physical delay and the chemical delay needs to be done in a fraction of second. Usually the physical delay time period will be higher than the chemical delay because the chemical energy will happen in fraction of time, but the physical process will take some time. Those analysis is very minute, and you need to go for a detailed thing that we can do. You can also do a lot of optimization, the simulation activity, modeling activity. Then you can take that into a real practice. Uh, when I say it's a physical delay or physical process, so the fuel spray atomization, that is the physical delay, and the evaporation takes some time. Okay, for the atomization to take place, evaporation to take place, and mixing of the fuel vapor with cylinder air. Okay, the air in the combustion chamber. It takes some time. The time is nothing but the delay or the physical delay. And again, the good atomization requires high pressure, small injector. It needs to have, for a good atomization, you need to have the high fuel injection pressure. That's why the injection pressure of diesel is going to be higher. It is coming nowadays up to 2500 bar in the case of a Toyota engines. And Initially it started with 1,200 bar. Now they're reaching towards 1,800 bar. Now this still many of the vehicles like Toyota they're going up to 2,500 bar. So that this type of increasing the increase compressor, you're going to get a good atomization as well. And here you're also going to have the small injector hole diameter, and this will also optimize optimum fuel viscosity, because the viscosity of it will also be much more better. If you have high viscosity, what happens is the delay will be higher. Okay, because fuel density should be to a level. Otherwise, it takes some time for the combustion to take place, which means still it will increase the physical delay. And even the cylinder pressure will also contribute to the physical delay. And the rate of evaporation of the fuel droplets is also depending upon. This also depends on the droplet diameter, velocity at which it travels, the fuel nature, and volatility of the fuel, the pressure and temperature of the air. And the next is chemical process or a chemical delay. The auto ignition phenomenon is going to happen in the premixed fuel air. So here chemical reaction will happen in air and fuel, that will happen during the premixed stage. The delay time are going to be more, that will be playing a vital role for it ignition delay. So here in the case of a diesel engine, it is going to be heterogeneous, whereas in the case of gasoline, it is homogeneous in nature. That's why nowadays we are also having HCCA engine, homogeneously charged compression ignition engine, to have the uniform flow of combustion in the case of diesel engine also. Okay. So this ignition delay is a characteristics of a fuel. It is based on the C10 number. We have the octane number in the case of a gasoline engine. In the case of diesel, we have a C10 number. So when the C10, if you have a low C10 fuel, the ignition delay is going to be longer. Okay. And most of the injected fuel is going to get accumulated in the cylinder before auto ignition. So this will also lead to a rapid combustion. Okay, so that's why you need to have the high octane C10 number. There is almost similar phenomenon in the case of a gasoline engine also. But there you have the octane number. I told you, if you have high octane number, you can also avoid the knocking. So here, if you have high C10 number, you can avoid the more time for the ignition delay. So what happens when you have more ignition delay? This may accumulate more fuel in the cylinder, and before auto ignition or the self ignition going to take place, what that will also lead to a abnormal rapid combustion also. Again, this also leads to a knocking. Okay, also leads to knocking. I'm not saying knocking, but I told you the knocking is less affected in case of a diesel than that of a gasoline. But still, you're going to get the diesel knock. That will happen only under extreme cases. Uh, but uh, but if you reduce the ignition delay, it is not going to happen. So some hardware design factors is also going to affect the ignition delay time. First one is injection timing. At normal injection engine condition, the minimum delay occurs when the start of injection. It will happen before top dead center 10 to 15 degree. So before this, or earlier to this, when you start injecting the fuel, then it may increase the ignition delay time, and may also result in high ignition delay period also. And again, the quantity of the fuel needs to be injected. For a case of diesel engine, the air is not throttled like in the case of gasoline engine. So the load is going to be varied only by changing the amount of fuel going to get injected. So if you inject high quantity of fuel, then that may also lead to a high delay period. So the optimum quantity of injection should be there. And that will also increase the brake minimum pressure of the engine. And again, the air inlet and the inlet air is going to have the temperature and pressure, and an increase in not either an increase in either the increase of either intake pressure or the temperature will result in decrease in ignition delay. Here what happens? You also have the exhaust gas recirculation, okay, EGR. When you use the exhaust gas recirculation, your here air and fuel gets the exhaust gas recirculation and sorry, not air and fuel. The exhaust gas recirculation is going to get mixed with the air. That will increase the temperature of the incoming air itself. Okay. When you increase the incoming air temperature, your ignition delay is going to be lesser. Again, the diesel engine is already having the high compression ratio. All this will reduce the ignition delay time. When you have less ignition delay time, you have no knocking or nil knocking in the case of a diesel engine. But the phenomenon is going to be completely different in the case of a gasoline engine. Yeah. So this is the graph showing a CTN number versus octane number. The octane number and CTN number of a fuel are inversely correlated between each other. So, this is the final thing that you need to keep in mind. Gasoline is a poor diesel fuel, and vice versa. So, for a gasoline engine, when you use a diesel fuel, gasoline is a poor diesel fuel, and again, the diesel is a poor gasoline fuel. Again, it is vice versa also. Higher the CTN number, what happens? You have a lot of advantages. I will explain that with the help of a graph. So when you have high CTN number, your ignition delay is going to be lesser, and again, that ignition delay you're going to compare with the brake mean effective pressure of the engine. But the same brake mean effective pressure of the engine, you need to have the less ignition delay for the normal combustion to take place. That will happen when you are having the high CTN number. Similarly, because of a gasoline engine, and the ignition delay or the knocking can be reduced by increasing the number of the fuel, same brake mean of the pressure in the knocking phenomenon. This is for a naturally aspirated engine having the pressure of 103 kilopascal. So how the ignition delay is going to vary. The brake mean effective pressure of the engine is going to get increased. The ignition delay is also going to be less. So brake mean effective pressure at high RPM, okay, even at a high RPM, when you say when the engine is running in high RPM, you get high brake mean effective pressure. When the engine is running in high RPM and high mean effective pressure, brake mean effective pressure, the delay period is also going to be lower. But there is also a quite interesting phenomenon with respect to brake mean effective pressure. The highest speed you get in the case of a gasoline instead of a diesel, when that is going to be in the higher, it doesn't mean that the brake mean effective pressure should be higher with respect to it. There is no ground rule that the brake mean effective pressure will increase with respect to the increase in diesel, but there with respect to the speed. But yes, the brake mean effective pressure of the engine will get increased. But at the same time, when you're comparing the diesel with respect to the gasoline, the brake mean effective pressure of diesel is going to be higher. It means the brake power of the engine is going to be higher for a diesel, and the thermal efficiency is going to be higher for a diesel. But the gasoline can be operated at higher RPM also. Okay, it can go higher RPM than that of a diesel. But you see, but brake main pressure is not that much higher as that of a diesel, and brake power is not that much higher than the diesel, and then the efficiency is also not higher than that of a diesel. So this is quite interesting phenomenon between diesel and